So I've given you a drawing, and we're trying to figure out the total Laplace. Now, okay, so we know, and let's do some colors. So we know the standard unit step starts at 0, goes up to 1 at time 0. And so please do not get confused. I'm going to use u of t even though the table calls the unit step u of t. There are only 26 letters in the alphabet. Okay? I can't use different letters for every different thing. So you'll see that in the textbook they use US and UR. I feel that it is very easy to understand what I'm looking for given the context of what I'm asking for. So this is kind of the unit step. And you'll see that this has a line in the table, right? So it has, actually, let me just make sure that that color is a bit more legible. So in the table, this is f of t, and this is f of s. So f of t is, they'll say u of t, right? And f of s is 1 over s. And then a little bit down in the table, you'll also find that there's this reference to f of t minus d, and you'll find this very useful rule lower down in the table that says how to handle x-axis translation using the Laplace transform, or let's say t-axis translation. And you'll remember that your first instinct was already right. If I want to move this unit step, if I want to move that so that it now occurs here, matching up with that first line at 1, then I'm going to need u of t minus 1. Is that making sense to everybody? Okay. I also know that because of this Laplace translation rule, I can very easily handle translated versions of the signal, right? Because if I know what the function is, if I see that it's being translated, if I see this negative over here, so that's the clue. If there's a function which has its time axis translated, I'm immediately thinking of this rule in the table that says, okay, I don't actually have to have the Laplace transform of this in the table. I can just look at the untranslated version, right? And see what that looks like in the table. So I know that that's going to be 1 over s times e to the minus s. That's what that contribution is going to be of this step up, okay? Now, again, imagine that I told you that this was the entire problem. Okay, if we just zoom in far enough, now we have a function that starts at 1 and then goes down to 0. Okay? What does that function look like? So it's minus, or 1 minus u of t minus 2. Does that make sense? So that function, just the one that goes from 1 down to 0, is 1 minus whatever, okay? But we're already building a function. We're already here, right? We already have u of t minus 1. Now if I want to translate even further, as I go on, as I translate that to that point, right, I'm going to have t minus 2, but we said that actually we're going to have minus u at t minus 2. Now, I hope you can kind of see the pattern now, because if I look at that and I see another one coming, and actually if I just had this, so u of t minus 1 u of t minus 1 minus u of t minus 2, I would have a single pulse input. Okay, so we see it's a step up followed by a step down. And in fact, at this point I'm actually done because I can think of this as being a translated version of that function. So I don't need really to keep building here because I can just see, oh well, I know what that looks like. It's a step up minus a step down. And then I'm going to take exactly those two steps, translate them by 3 units, and I'll see what the step looks like further down. But we can keep going just so that we can see the pattern. We're going to have another one here, so that I'm going to write down here plus u t minus 3 minus u t minus 4. Okay, so another thing that I want to show you is that it's very, very easy to check that I'm doing the right thing. You can actually build this function in GeoGebra. Okay, so I've now defined this function u of x, and I can now build my functions here just using, I'm just going to, unfortunately, I haven't found an easy way to just rename x to t. So I'm just going to use x. But so remember what we have. We've got u of t minus 1 minus u of t minus 2 plus u of t plus 3 minus 3 minus u of t minus 4. And so let's see what that looks like, because now we can kind of confirm that we're doing stuff right. So if we just plot that, notice that that's doing the right thing. Unfortunately, GeoGebra is kind of trying to be very mathematically correct, so it doesn't draw the line connecting, and you know, the math guys hate that. They hate drawing a connecting line where there is no data. I'm fine with it because it makes it a little bit easier to read. Just keep that in mind. I can actually build a full set of functions, right? So remember we had the u stepping up at 1. We now have another u which steps at 2, and look at that, that's now taken it down. And we have another u that goes up at 3, and we have another u that steps down at 4. So it looks like we have done an A1 job. Okay, so I like GeoGebra for this quick kind of plotting stuff because it's also really easy to do things like this, where it'll allow you to put in a little slider and you can kind of manipulate stuff very easily. So unfortunately the screen isn't very big, but you'll see that it kind of maps out that D, so I can make that anything I want. Now you can see that if I just move the time at which the step happens, I'm kind of adding all those different things together. Now in the textbook, and I know that students actually have a lot of trouble with this way of representation. In the textbook they draw these interesting diagrams that look like this. So they kind of draw something like this. So the textbook's diagram looks something like this. And then they're saying, okay, so this is the one function, this is the other function, and then this is like the sum of those two functions. Whatever helps you to understand how these functions are built is cool with me. So I don't really care, you don't have to represent it this way. I find it really easy, and I think it is a very valuable skill in this subject to visualize the original functions and be able to mentally add them together. We're going to need this later on in the course as well. So it is very worth it to train that way of doing things, but I'm also going to show you a completely never fail method where you can just study it and like you don't have to understand anything. Okay. Like this is literally true. Okay, so I've developed this technique over many, many years, and it relies on a basic insight that once you've done one of these examples, you kind of see a very strong pattern, right? That at every point, so there's this time here, happens at every point where something happens. So there's a 1 over there, there's a 1 over there. That's because something happened at time 1, right? Then at time 2, something else happened. There's the next time that something happened, and we're looking for a shifted function which has a 2 in its shift, right? And then the next time something happens is at 3, and there's that 3, and then the next time something happens is at 4, and there's that 4. And so we see that there's this general pattern. These unit functions have been chosen exactly the way they have, exactly for this reason. They are 0 at times less than 0. In exactly the reason, because when we shift them, they will never have an effect when we add, before the time that they have an effect, right? Remember, I'm trying to express a complicated function as the sum of some simpler functions. And look how useful it is that the unit step is 0 for times less than 0. It means that I can add that 0 infinitely many times and not have any effect to the left of that time. Okay, so this is a very important property. It allows us to say that I can literally just move from the left to the right. I don't need to do any special stuff. I don't need to kind of combine these functions very subtly like I had to do when I was solving differential equations and I had to kind of solve for unknown coefficients, right? I can follow a rule. I can read the graph from left to right. And I know that if something happens, I can add these functions and it won't have any effect to any of the functions that I've written down so far. It won't change anything to the left of the time that it happens. Is that making sense? So this is already really cool because I can just go left to right, okay? So I go left to right, I say, okay, first time something happens is at 1, second time something happens is at 2, 3, and 4. So I know I'm going to need exactly 4 functions to capture this set of changes, right? I know what their shifts are because they will be shifted by exactly the amount of time that I need to move them to the place where they're affecting stuff. I write them down from the left to right, and the general rule that you can just study, right, is that any one of these, anything that is, this example is what is known as piecewise constant. Okay? Any piecewise constant function can be expressed as the sum of unit steps with changes in the magnitude, in the signal as coefficient, and the time at which that change occurs as the shift. And that's the whole of the rule. You just add a lot of those together, okay? So does this work for the example that we have? Yes, because that first change is 1. This is minus 1, right? That coefficient is minus 1 change, the change going from left to right. Okay, so each time I write one of these deltas, I'm saying there's a left-hand side and there's a right-hand side of that change. And I've got a plus 1 change over here, I've got a minus 1 change over here. Then I've got another plus 1 change, I've got another minus 1 change. Doesn't have to be 1, can be 5, can be 10, can be 100, can be 0.1, right? Can be negative, can go negative, but the key is that you're going to encode the changes, not the absolute values, right? And you're going to express it that way. Now there's a second class of common functions, and these are, and I'm going to do an example here of that kind of function. Let's just do a very similar example to the one that we have. This one actually is also in the textbook, but let's just take a triangle wave like this. So let's say that goes up to 1. Let's say again, these are at times 1, 2, and 3. So the peak there is at time 2. And we're going to do the same thing now, except we're going to use ramp signals as our building blocks. Okay? And so ramp signals can be used to handle any piecewise linear function without discontinuities. So for continuous piecewise linear functions, we can always express that as the sum of ramp signals. Now, ramp signals, you'll remember, they look like this. Okay, and the unit ramp, very importantly, has a slope of 1. Now, you can see why we've defined it that way, because the reason why we have these standard functions is so that we can do the thing that I'm doing now, right? We've defined the unit step so that we can multiply by the size of the change in order to model a moving or a signal that has these discontinuities just by multiplying by the size of the discontinuity. And we've defined the ramp to have unit slope so that we can say all I need to do is figure out what this slope change is. Now, very importantly, we're going to do the same trick that we did with the so we're going to do the same trick, but our changes are going to be changes in slope. Okay, so let's just look at again what those signals look like, right? So I take this and I can see, leveraging some of the intuition that we built in the first problem, we can see that clearly it's got the same thing of being 0 up to time 0. And so I can move that base signal, let me just do that in a different color. So I can move this ramp signal, so this thing we'll call R of t. Right? And let's just say that we want to model a change in slope at a particular time. Again, if we translate that same signals to coincide with 1, I'm going to have R of t minus 1. Does that make sense? And again, we notice this time, so we notice that the time at which the slope changes corresponds to the time that we translated the ramp by. Okay? And so we can see that that first slope change is going to be modeled by a ramp that starts at t1. Now, the ramps are a little bit tricky, okay, because they continue along. Remember, by the time that I've just done that one ramp, if this ramp is the only thing that I have, right, then it starts at 0 there, and then it continues moving up forever. Up and up and up and up, okay? Even just to move that, if I wanted the signal to stop like that, that would still be a slope change. I'd still need 2 ramps to model that behavior, right? Because I'm going up at 1 unit per unit time. To get to 0, I need to subtract 1 unit per unit time of slope. Okay, and so we're reasoning here through slope changes. This is why I draw these slope changes this way, where I'm saying, again, we've got the same rule here. We've got times, and now we've got slope changes. Now we've got 2 slope changes, or we've got 1, 2, 3 slope changes. And so we expect that we're going to use 3 ramp functions added together to get this behavior. Again, we can now say this slope change, that slope change will be modeled by R of t minus 1. This slope change will be modeled by minus 2 r of t minus 2. Does everybody see why we have a 2-unit slope change going down? Okay, because let's just work this out. This slope here is 1. This slope is minus 1. Okay, and if we can actually, if you really want to, I feel that it's a little bit too mechanical, but you can build up a little table of slopes, right? So you can say, so that's the slope table, okay, in each of these regions. So there's a 0 slope in the first region, there's a 1 slope in the second region, there's a minus 1 slope in the third region, and there's a 0 slope in the last region. Is everybody following me? Cool. And so the changes are the difference between the elements in the slope table, right minus left. Okay, because we're moving from left to right, so we're going from a 0 slope to a 1 slope. That's a delta 1 of 1. And then here we're going from 1 to minus 1. The difference there is minus 2. Okay, so to get from 1 to minus 1, I have to do delta 2 is minus 2. And then I can't forget that I still have to get back to 0 again. Because at that point, if we've just got those 2, we're going down now forever at a rate of minus 1. And so we've got to get back, and here delta 3 is 1 again. So because I want to go from minus 1 to 0. And we can see that in general, I can now express any continuous piecewise linear function as the sum of ramp functions in this way. The sum of the change in slope times the ramp function translated by the time at which that change in slope occurs. So, how then do we handle cases where I have both things happening at the same time, where I have discontinuities and changes in slope? I simply add them together. Very, very easy. Okay, so you've got 2 rules to learn, and you can learn these rules straight up. There's a notebook in which I expand on this, where I show you the kind of general rule, but in general, the final wrap-up is, for every discontinuity, you're going to have one term that references a step function. And for every change in slope, you're going to have one term that references a ramp function. So check the notebook. Also check, there's a worked test problem where I do exactly this method, but on a test problem that includes changes in slope and in and discontinuities. Yes?
Can you use the ramp function to model the piecewise constant because you've got a change in slope?
No.
On the second one?
No. That's a very, very good question. We have a question here. Why can't we use the ramp function for everything? Why can't we just have a ramp function with a super huge slope? Because a ramp function with a super huge slope conceptually does not exist to the right of the point at which it ramps up infinitely. And so there's no way for us to have that signal. So this is kind of why the mathematicians don't want you to draw that line up, right? Like it's not actually a line up, it's a discontinuity. And the ramp function is continuous, and there's no combination of continuous functions. You can never combine continuous functions to obtain a discontinuous function.
Because they happen at the same time.
That innate discontinuity. The last thing I want to say is an interesting thought experiment is I want you to notice that the ramp function, if you think of the ramp function as being the integral of the step function, you can actually think of this rule being redundant because we just use the same rule on the derivative. Okay, so in exactly the same way, I've done the slope separately, but if you think about that, this signal that I've drawn here, you could have drawn that as that signal. That's the derivative of that signal. The derivative is just a combination of steps. Now, I'm going to come back to this a couple of times because I want you to be very, very good at sketching integrals and derivatives.